Okay, thanks. So yeah, I'm going to speak about this paper that we have on the old-fashioned Blotto game. That was the original one with untouchable resources, so the very oldest one. So it's been introduced as a cache in 1 century ago, actually, by Boyle. But before, I just want to say that this is a joint work with my friend and colleague, Philippe Rigollet from MIT, and Thibaut Gouic from Marseille. And so as we said, this Blotto paper was described in 1 century ago by Blotto as kind of the one of the founding paper on game theory. But quite surprisingly, if you look at the at this game, the solution, description of the solution, and computation of the solution of this game is still open, or was still open in a large variety of parameters. But let me describe this game again, if you missed the previous talk, and so I will have the same notation. So this Blotto game is still a game between two generals, two players, A and B, and they both have they both competing on a number of battlefields. Okay, they're competing on here in this example 3 battlefields, and each of the generals have a number of troops, TA and TB. And this is continuous, right? It's a continuous amount of troops, TA for player A and TB for player B. And at the same time, just as the previous talk, each general decides to allocate some of those troops to each battlefield. Okay, so so those numbers here could be not necessarily integer, right? It could be any real number. And the winner of the battlefield, as before, is the general that puts the most strength into this battlefield. So here, in this example, the General B is going to win the first 2 battlefields, and General A is going to win the last one, okay, because they have more troops than the other one. So we end up in this situation, and then the question is about the utility that each player gets from this outcome, and we're going to assume that each battlefield has a different value for player, okay? So here, in this example, I'm going to assume that the first 2 battlefields have value VB1 and VB2 for player B, and VA3 for player A. Okay, and those numbers are known, of course, to each player. And the total utility of this Blotto game is simply the sum of the values of the battlefields that you won. Okay, so that's the sketch of the Blotto game, a typical Blotto game. And if I want to give more formalism, I could say that, okay, Blotto game, as I said before, is between 2 players, A and B. They have budget. I'm going to assume that budget of A is bigger than the budget of B. And there are n battlefields they are competing on. The value of those battlefields can be different from battlefields to battlefields and different from each player. Okay, player A can have higher values for this battlefield and lower for this other one. It's in full generality. The only assumption that I'm going to make, it's purely technical. It's just a matter of renormalization. We're going to assume that the sum of the values of battlefields is equal to 1 for each player. But that's purely a question of normalization. It's not an assumption at all, actually. And in this Blotto game, there have been many papers working on this problem with different set of assumptions, restricting assumptions. The first one is you can assume that the budget are symmetric. Okay, they have the same budget. So that's called the symmetric budget. The other type of assumption is that each battlefield has the same value for each. Say again. So each player has the same value for different battlefields. So that we call symmetric values. That was the case in the previous talk, actually. And in this case, as mentioned before, we'll end up in a zero-sum game. And the simplest variance of this Blotto game will be like what we call homogeneous values, is when all battlefields have the same value to all players. Okay, so that's the kind of assumption that has been studied in the literature so far, because it simplifies some of the analysis. But if you look at the state of the art, so Blotto was introduced 1 century ago, so I had many papers on this problem, on the continuous Blotto. And you can see that most of the papers focused on the symmetric value case, as we said before, because then it's a zero-sum game, so the concept of solution is quite clear. But there was always restricting assumption on the budget, on the values, on the number of battlefields, or other type of restriction. And what we did in this paper is actually we removed all of those assumptions. We look at the general Blotto games that I described before, and we characterize and compute the equilibrium of this game. So the question that you should ask when you see these slides 1 century ago, and it's still an open question, is what is the difficulty of a Blotto game? What is taking so long to solve this problem? And the reason is the following. So in this zero-sum game, we have to play a mixed strategy, as mentioned before. Okay, so in mixed strategy, so we have player A that's going to allocate a random vector, is going to choose a random allocation vector, each xa1, xan, that's the strengths put on each of the battlefield, such that the budget constraint is satisfied. Okay, so the sum of the strengths must be smaller than TA, total budget. But of course, since it's quite clear that the optimal strategy will saturate this constraint, always. So at the end, a mixed strategy in Blotto game is a random allocation vector, xa1, xan, such that the sum of each component is equal to TA almost surely. And this is this constraint that must almost surely, which is difficult. Because actually, when you're thinking of almost sure constraint, it's basically as if for each omega of your probability space, you have a different constraint. So this almost sure constraint is making the Blotto game very, very difficult because it's as if you had an infinite number of constraints to satisfy at the same time. So that's why it's difficult. So if it's difficult, what you want to do is we want to get rid of this difficulty. So instead of looking at the almost sure constraint, some people looked at the game where instead of having this almost sure, we have the constraint in expectation. And this game where the constraint is in expectation and not almost sure is called the Lotto game, without the B. And this is a much simpler problem, because we have only one constraint for each player. And in this game, the Lotto game, we can see that, so 1 year ago, Gouic and Robertson, they gave actually, they describe the equilibrium in this Lotto game. And in the equilibrium described is the following. So the set of battlefields are going to be partitioned into two sets. The sets where player A values more this battlefield than the other one, thanks. And so I'm going to call n gamma, the set of battlefields, such that player A values its battlefields gamma times more than player B. Okay? So here, in this case, I'm going to assume that it's the last two battlefields. Gamma is a parameter that's going to be computed later on. Okay? So it's just one parameter. There is another parameter, lambda, that's going to pop up in the next click, but it's also another parameter that we can compute. And based on this very simple decomposition, Gouic and Robertson gave the optimal, if you are in the sum game, the optimal strategy, otherwise an equilibrium of the game, as follows, an explicit one. They say that the marginals that each player should play are those marginals. Okay, so this is not really important. The actual form of it is not really important for you. What is really important to notice is that for player A is going to allocate some strengths on the battlefields in n gamma. It's going to pick it uniformly at random over some interval between 0 and some length Li. And on the battlefields that do not really care, those are not in n gamma, you're going to play a mixture of a Dirac mass. So with some probability, it's going to put zero strength on this battlefield. And with the remaining probability, it's going to pick, again, a random number uniformly at random over a different length. Okay, so at the end, what we get is that the optimal solution of the Lotto game, where the constraint is an expectation, is either you're playing on the battlefield uniformly at random, or you're using a mixture of Dirac mass at 0 and uniform distribution. The length of those uniform distribution, you can compute them by solving some equation. It's not really important. What matters is just that it's either uniform or a mixture of Dirac mass and a uniform. That's all you need to know. So now the question is, that is the solution for the Lotto problem. The issue, of course, is that if you implement independently each of this distribution here, each of these marginals, the budget constraints will be violated. So the question we ask is it possible to have the same marginals of the Lotto solution, but where the constraint, the budget constraint, is satisfied almost surely? Because if we can couple the uniform distribution, the distribution of on the different battlefields, such that their sum is equal to the budget almost surely, then we know for sure, because the Lotto game is a game which is more complicated than the Lotto game, we know that we'll have a solution of the Blotto game. So if we can find a coupling between all the marginals, all the allocation between each battlefield, such that the sum of the allocation is equal to the budget almost surely, then we will have a solution of the Blotto game. So that's the question we should ask. Now, more generally, the question that we want to answer is the following. if I give you some random variables, some distribution, x1, xn, so you have n random variables, can you couple them such that the sum is equal almost surely to their expectation? Or said otherwise, can you find the coupling between these n random variables such that the variance of the sum is 0? So that's the question. And actually, the good thing is that there are people in statistics, or in probability, that look at this very specific problem. Given a random variable, can you find a coupling between them such that the variance is 0? The variance of the sum is 0. And this is called joint mixability. And we have these results that came from 6 or 2 years ago from Wang and Wang or Zimin that basically gives us what we need. It says that if you're taking n random variables, which have a density, monotone decreasing density, and supported on an interval, then we can jointly mix them, meaning that we can find a coupling such that their sum is, the variance of the sum is 0. The sum is always equal to the budget. If and only if this condition here holds. And in our case, it just means that the maximum length is smaller than the budget. So that's just what we need. Just what we need to have. So that's a very, very strong result. And so what we did actually is the first part of the paper was to say, well, we have the Lotto solution in expectation. We have the marginal in expectation. We want to find the marginal in almost surely. We have this result that says that if we have monotonically decreasing density, you can couple your marginals to get the same constraint in almost surely. So let's use those two black box tools that we have, and we can claim that we can transform the Lotto solution into a Blotto solution if this condition is satisfied. So in the case of symmetric value, okay, remember when each player has in the zero-sum game, if you do the computation again, you can see that this implies that the condition says that the maximal value that a player puts on player A puts on the battlefield should be smaller than 1/2. That's the condition. And for player B, it means that the maximal value for him should be smaller than gamma over 2. Okay, and then if this happens, then it's doable. And if you think about it, since the sum of the VA is equal to 1, Vmax is smaller than 1 over n, so this means that the budget of player B, which is smaller than budget of player A, must not be arbitrarily too small compared to the budget of A. Okay, the constraint that we need is something that says that the budget of A should be, budget of B should be bigger than 2 to the n, 2 divided by n budget of A. So it's quite a reasonable assumption. So basically, that's the first result of the paper that says, if you take the Lotto solution, the explicit Lotto solution, you can transform them into a Blotto solution if and only if this result holds. That's in the symmetric value case. This assumption, actually, as I said before, is quite mild, actually. It's quite reasonable. It's a balancedness assumption, which is quite reasonable. And we have the same results, typically the same kind of results with Nash equilibria for asymmetric value case. 5 minutes, perfect. So here there is a major twist in this slide. It says that the Lotto solution can be transformed into a Blotto solution. The question is, how can we do that? Because the proof of the results of Wang and Zimin are highly non-constructive. So the question is, can we find an algorithmic solution that says, well, you can find, this is how you can couple your random variables. So that's the question. Can you find an algorithmic solution that outputs the coupling? And that's what we want to do next. That's the next part of the talk. So let's go back again. So what we want to do is, so we have all of the marginals, x1, xn. We know that it's a mixture of a Dirac mass and a uniform distribution, all of them. And we want to find the coupling between them so that the variance of the sum is 0. Okay? So basically, we end up with finding a coupling, let's call it gamma, such that this integral is equal to 0. Okay, we want to minimize, at the end, what we want to do is we want to minimize over the set of all coupling the variance, the sum of the xn square. So there is a very naive way to do that. It's, well, let's do it very simply. Just discretize all the marginals up to epsilon, and then we have a finite problem, just solve it. The issue is that since we have n random variables, the size of the coupling will be of 1 over epsilon to the n. So obviously, I will not be able to find an efficient algorithm if I'm using this strategy. So what I want to do is I want to reduce my problem for n marginals to only 4 marginals. And we have a way to do that. And that's the whole point of the paper, actually, is showing how we can solve this problem with a complexity which is not in 1 over epsilon to the n, but 1 over epsilon to the 4. And how we can do that? there is a bunch of tricks, algorithmic trick and geometric trick. The first one is actually say, well, I will be able to construct this coupling between random variables. You remember that they are a mixture of Dirac mass and a uniform distribution. I can do it only if I have only one mixture of Dirac mass and uniform. If I have two Dirac mass and uniform, I don't know how to do it, to be honest. So here, the first step of the algorithm is say, well, instead of having a coupling between n random variables that can be a mixture of Dirac mass and a uniform, we first reduce the problem by using Carat-Theodori theorem in parametric space to say, well, I can first compute a mixture of couplings where only one of them is a mixture of Dirac mass and uniform. So using this Carat-Theodori theorem, I can show that only one of my marginals can be a mixture between a Dirac and a uniform. So at the end, the second step is I still have n random variables, and I want only 4 of them. But here, in this example, so I have, here I'm going to assume that n equals 6. So 6, so I have one mixture of Dirac mass and uniform and 5 uniform. And now I have this result. I mean, if I'm doing the computation, if you do the linear algebra, it says that you can actually merge iteratively the uniform distribution into another one. So here I can take the first two, and I can merge them into a third one, and so on and so forth. I can merge 2 by 2 the uniform distribution by, sorry. I can merge those uniform distribution and reducing the size of my problem by 1 at each time, still respecting the budget constraint. So at the end, I can do this iteratively, and I will end up with only 4 random variables, 3 uniforms and 1 Dirac mass, and 1 mixture between Dirac mass and a uniform distribution. And this, I know how to do it. So now I end up with a problem in dimension 4, 3 uniforms and 1 Dirac mass that I need to couple together. And to do that, I'm going to use, I could say, well, you have the linear program to solve in dimension 4. You could use any solver of this linear program. But actually, we cannot control precisely the performance of these linear programs. So instead, we use Synchron iteration, Synchron algorithm. Synchron algorithm is an algorithm that basically says, computes a coupling, an optimal coupling between random variables that minimize some cost. But here, I just want to find a coupling. So we're going to use Synchron algorithm as a black box, just to find the coupling between those 4 random variables. The only issue is that we have to modify it because here I have a constraint on the diagonals for my random variables. That's the budget constraint. But I can still use a Synchron algorithm, a modified version of Synchron algorithm, to solve this problem. And at the end, when you make all the computation of the error we make, we can show that this algorithm, we can compute the epsilon Nash equilibrium in the computation time of n squared. That's the first 2 reduction step, plus a complexity in 1 over epsilon to the 4. And actually, it works very well. We have this app, this small app. It's very ugly. We definitely have to do it better. But you can play Blotto game against the algorithm if you want to try. And I guess you will fail. You will lose. Thanks.
Time for one question.
Yeah. No, the proof of the coupling is actually purely is by compactness. Saying, well, they're saying, well, we have those random variables, we slice them in small size of epsilon, and then we're making those small changes, and let's say that the error we make is of size square root of epsilon or something like this. And when we take epsilon to 0, this proves the existence of the coupling. They managed to prove the existence of the coupling, but not with an algorithmic manner. It's really a question of compactness of the set of couplings, and they show that there exists one.
So I assume that you make a subtraction of the problem algorithmic. How far away is it to make the whole?
That's a good question, actually. If we can find, based on this kind of techniques, can we find an algorithmic solution to the coupling, the general coupling question? It's a very good question. I haven't thought about it, but We used a lot the fact that here we have only 4 marginals and those are uniform. But I guess if I'm using the sync on, it should, it's a very good question. I should look into it. Yeah.